This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
My pleasure to introduce for this first speaker, Ed Barnes from Virginia Tech. Please, take it away, Ed.
Thanks, Ben. Can you hear me okay? In the back, it's fine? Great. Yeah, so as you can see, I'm not Sofia Economou. So we made the 2.5-day journey from Virginia Tech all the way to here, but then she got sick. So she's currently in the hotel room recuperating. So the slides are hers, but you'll have to hear my voice. So yeah, I'm going to talk about adaptive variational algorithms. So in the first part of the talk, I'll just give you a quick overview of the work that we did starting 5 years ago, and many modifications and updates since that original paper came out on adapt VQE. And then I'll talk a bit about applying those methods to Gibbs state preparation, which has applications, of course, across many different aspects of algorithms and machine learning, et cetera. And then if there's time at the end of the talk, I'll mention a different approach to variational algorithms that's based on pulses rather than gates. Yeah, so variational quantum eigensolvers are not the only application by any means of the stuff I'll talk about, but this is sort of like the natural example problem to keep in mind as I talk about things. I'm not going to go over this. I assume we've all seen it enough already in this conference and elsewhere. Of course, the important thing for this talk will be how you actually prepare, how do you actually construct or choose these circuits that you use to define your trial states on the quantum device. So going back 7 or 8 years now, one approach to this is to just pick circuits based on gates that are easy to implement in your favorite hardware. So this is a hardware efficient type ansatz. The nice thing about this approach is that the gates are automatically tailored to the device. You know how to do them with pretty good accuracy. But as we all know, that this kind of approach can be rather inefficient, and it can be plagued by barren plateaus. And which just means to say that they're essentially difficult to optimize. So an important theme in this talk will be this idea of problem awareness, and then I'll go even further and talk about problem tailoredness in the ansatz, where instead of using random circuits, which is essentially what a hardware efficient approach is, use circuits that know something about the problem that you're trying to solve. If you're trying to simulate some quantum many-body problem, take some information about that problem and insert that into your circuit. And this can mean incorporating things like symmetries, particle numbers, spin symmetries, et cetera, which of course depends on the problem you're trying to solve. Spatial locality, translation symmetry, stuff like that can also be taken into account. This can help avoid issues with optimization, as I'll discuss in detail, and can also lead to shorter circuits. You spend more time in the part of the Hilbert space that you actually care about. So in the case where you're trying to solve some many-body fermionic problem, the first step, of course, is to map your Hamiltonian onto your quantum device. In this talk, whenever I talk about fermionic problems, I'm going to always have in mind the Jordan-Wigner mapping for simplicity. And if you want to build a problem-aware ansatz for a fermionic problem like a molecule, which will be described by a Hamiltonian like this, you can build your circuit based on operators that you see in the Hamiltonian, like these singles operators and these doubles operators involving two fermions. So this was the approach that was taken in the first paper on the variational quantum eigensolver 10 years ago now, where they used this approach called UCCSD to construct their parametrized circuit for trial states. This approach is chemistry inspired, so UCCSD is something which has already been used in the quantum chemistry community for a long time, and it was kind of natural to try to apply it to this quantum computing problem. So the nice aspects of this ansatz is that it does know something about the problem you're trying to solve. In particular, it knows about the symmetries, like spin symmetry, particle number. But it still leads to rather really long circuits. It's still quite impractical in that sense. Many CNOT gates. And there are some inconsistencies as well when you think about how you actually trotterize. So this ansatz is like one big exponential where you throw in all your singles and doubles fermionic operators into one exponent. To actually run that on a quantum computer, you have to somehow break up that exponent into pieces, and there's some ambiguities in how you actually define the ansatz at that point. And we've shown in this paper from a couple of years ago now that you can oftentimes end up with things that don't work very well at all. But this is an approach that's been popular in experiments demonstrating VQEs on various types of hardware. But this is still not good enough from our perspective, so we want to find a way to generate ansatz which are short, expressive, meaning that they can actually represent the state that you want to represent on your quantum computer, and they should be trainable. You can steer that state exactly to where you want it to go. So this was the motivation behind developing this approach that we called ADAPT VQE, which first appeared about 5 years ago now. And the basic idea here, so this ADAPT stands for Adaptive Problem-Tailored Variational Quantum Eigensolver. You start from some simple reference state. If it's a molecular problem, it's something like Hartree-Fock state typically. And you want to recognize the fact that quantum resources are precious, so only add as many operators as you need in the circuit and nothing more. So the idea is you want to add operators to your circuit one at a time in a way that's informed by the problem you're trying to solve. And you let the device and the problem tell you what operator to add at each step, instead of just picking something randomly up front. So one by one, you build out your circuit as the algorithm runs. So you learn the circuit that you want to use on the fly. Not just the parameters, but the actual operators appearing in it. So a very important ingredient in this sort of adaptive algorithm is what operators do you choose from when you build up the circuit. We call this the operator pool. And so you decide what the pool is up front. I'll mention a bit later what sort of choices are natural for different types of problems. So these operators are what appear in the exponent of some unitary. And for every operator that we add to our circuit, there will come with it some variational parameter theta that gives us additional flexibility at that point in the algorithm. So, and then the way that we decide which operator to add at a given point in the algorithm is by looking at its impact on the energy, the cost function, which is the energy in the case of VQEs typically. And so you can show that when you add on a trial basis one of the operators from your pool with its corresponding variational parameter theta, if you differentiate the cost function with respect to theta and set theta to 0, it's just the expectation value of the Hamiltonian with respect to that operator. So at each iteration of the algorithm, you can go and scan through your operator pool, look at this expectation value for each of those pool operators, and pick the one that gives you the biggest change in the cost function, add that to your ansatz, and then keep going. So that's the basic idea behind ADAPT. This is what the algorithm looks like overall. So your inputs are the Hamiltonian you're trying to find the energy eigenstate of. You want to provide also an initial state, like Hartree-Fock in the case of chemistry problems, and your operator pool, which needs more discussion. I'll come back to that. But then the way the algorithm works is that at every iteration of the algorithm, you go and you scan through all of these pool operators, measure the gradients, take the one that gives you the largest gradient, add that to your ansatz, check whether the ansatz is sufficiently converged given some threshold of the energy error. And if not, you just keep going, keep adding more operators until you get some, you satisfy some convergence threshold. So we initially tried this with some small molecules. This is an example with beryllium hydride. So this is comparing 3 different versions of ADAPT where we've set 3 different values of the threshold for when to truncate, when to stop the algorithm. So epsilon 1 is the coarsest choice, 0.1, and you can make it finer and finer, allowing the algorithm to keep running and getting better and better energy estimates. So we compare these 3 versions of ADAPT against UCCSD, just Hartree-Fock itself, and then the gray shaded area corresponds to when you reach chemical accuracy, which is considered sufficient for practical use. And you can see in these plots of the energy error versus the distance between the atoms that the adaptive algorithms are giving you much better performance compared to UCCSD, and of course, much better compared to Hartree-Fock. But what's also important is to look at how many variational parameters do you need to reach that level of performance. And here you can see that compared to UCCSD, which for this problem requires more than 120 parameters, you can get better accuracy for 1/3 of the parameters or even less. So this is showing us that this fixed ansatz UCCSD is very inefficient at solving this molecular problem, even though it knows some things about the problem that's being solved. And now you can also ask, okay, if I take this ansatz that ADAPT produces and I just rearrange the operators, how important is that arrangement of operators that ADAPT discovers in the course of its runtime? And that's what this plot is showing here. So the orange and blue curves correspond to the actual ADAPT ordering of operators in the circuit. versus various other ways that you could imagine ordering the operators, lexicographically, randomly, whatnot. But you can see that there's something really special about the way in which ADAPT chooses that operator ordering. You converge much more quickly to the solution compared to doing something more random. Okay, so now I want to come back and emphasize this distinction between problem-tailored and problem-aware. So problem-aware, I use that to mean the ansatz knows something about the symmetries of the problem, maybe a little bit more than that. But there's still a lot of important information that's missing in the ansatz in that context. And so these more problem-tailored ansatz kind of target that aspect of things. So for example, if I'm looking at a chemistry problem and I plot energy versus bond distance, I generate this dissociation curve. If I'm using UCCSD, I would use the same exact ansatz for every point along that dissociation curve. So for every separation between the atoms, it's the same ansatz. Whereas in ADAPT VQE, you tell me the separation between the atoms, it generates a circuit. You tell me a new separation between the atoms, it generates a new circuit for that particular aspect, that particular instance of the problem. So it's much more refined and targeted to the problem that you're trying to solve. So this algorithm ADAPT produces a compact tailored ansatz. The circuits are much shallower compared to these fixed circuit approaches. Now, an important question, of course, especially for this kind of audience, is the trainability of the algorithm. How well can you tune those parameters in the circuit to get at the state that you want? So this you can systematically study by taking the circuit that ADAPT produces for a given problem, and now just throw in random parameters instead of the way that ADAPT does it, which is to reuse previous optimal parameter values as the initial parameters for the next iteration of ADAPT. So instead of doing this recycling of the parameter values, which is the true way that ADAPT runs, that's the green curve here, you could just at every point in the circuit just throw in some initial random parameter values and try to optimize them and get down to the lowest energy you can. So those are what all these other dashes in the plot are showing you. So what this plot is showing is that if I throw in random parameters, I don't get a very good solution. The energy does not lower very much. And so what I'm actually seeing here is that the landscape is horrible. It's filled with local minima, and if I choose parameters in a stupid way, I'm going to get stuck in local minima very easily. But if I do this ADAPT recycling procedure where I reuse previous optimal parameter values at the next iteration of ADAPT, then I stay close to the global minimum in the landscape at all steps in the algorithm. So in this sense, ADAPT seems to be resistant to things like barren plateaus and local minima. And essentially what's going on here is that we are building our circuit on the fly in such a way that we are choosing the next operator to add to create a parameter landscape which is pleasant. And you're always close to the deepest or one of the deepest local minimum in the landscape by construction. So you never have to explore these barren regions that might be out there. And so this kind of leads to this idea of expressivity potential versus expressive circuits. So expressive circuits are just these huge circuits with lots of parameters, and you tune the parameters, you get many different wave functions, you kind of span all of Hilbert space or a big chunk of it. But that's not what we want here, because that's where you end up with barren plateaus and other optimization issues. Instead, we want to talk about expressivity potential, which is I have an algorithm that allows me to potentially create many different types of circuits. But in any given run of the algorithm, I get something which is very targeted to my specific problem. It's not, one instance of ADAPT is not very expressive in that sense. But on a whole, it's a very expressive algorithm, so it has expressivity potential. So yeah, random circuits can be very expressive, but very hard to optimize. A much better approach is to build an algorithm that has this sort of potential to express things, but not every state can be represented by one run of the algorithm. So how should we choose this operator pool? So we can still take into account things like symmetries, connectivity, locality of the Hamiltonian that we're trying to simulate, if it's a simulation type problem. For a fermionic problem, like a molecule, I can choose operators in the pool, which are fermionic singles and doubles operators, these same operators that appear in the Hamiltonian. This is what we did in the original ADAPT paper. But these can be hardware inefficient. They can, if you translate one of these fermionic operators to standard gates like C0 and single qubit gates, you can end up with a rather long circuit. So you can do other things as well, which kind of sort of balance this idea that you are including information about symmetries, et cetera, but you're also kind of being hardware aware. You You don't want to end up with each piece of the circuit being very long to implement on your given hardware. So you can actually have kind of a spectrum of pool operators for, say, a molecular problem. So you can think about the fermionic pool, like I was just discussing, made up of operators that appear in the Hamiltonian. Or you could look at qubit pools, as we call them, which are just Pauli strings of weight 4, which know much less about the symmetries of the problem you're trying to solve. But they're hardware friendly in the sense that each of these weight 4 Pauli strings can be implemented with a short circuit with just a few C-naughts. Or you could do something in between, which has some knowledge of the symmetries of the fermionic problem, but which is also kind of more hardware aware in the sense that it has weight 4 operators appearing in it. And this is called the qubit excitation pool, which was developed by some colleagues of ours at the University of Cambridge. So if you compare these, what you find is that the fermionic type pool that knows more about the problem you're trying to solve requires fewer parameters to reach the target state. Whereas if you use something which is more hardware efficient, like this qubit pool, it requires many more parameters to reach the target state. But if you look at the number of C-naughts in the final circuit that gets produced, you can actually win with these hardware efficient pools, even though you need many more parameters in the circuit. So there's a bit of a subtle trade-off there. And then you can also see that this intermediate pool, this qubit excitation pool, does somewhere in between in both cases. So you can do even better than all these three. So this was some work that was done by Mafalda Rameau, who will give a talk later this afternoon at 4:15. I encourage you to see her talk. I don't think she's going to talk about this particular piece of work, but it is related to these adaptive variational algorithms. So her idea was to take these qubit excitation pool operators and combine them pairwise into operators that have even more knowledge about the symmetries of the problem. And then you end up with a pool that she calls the coupled excitation operator pool, or the CEO pool, that when you write out each operator in terms of Pauli strings, it's a little bit more complicated looking compared to these qubit excitation pool operators. But overall, they give much better performance in terms of both the number of parameters to reach the target state and also the C-naught count of the final circuit. And so far, to my knowledge, this is the most efficient choice of pool you can make for a fermionic problem. So that was one example of a boost that we have given to ADAPT since it was formulated 5 years ago. Another improvement that we have made is to find ways to compress the circuit, which is to say, instead of adding one operator at a time, one operator per iteration of the algorithm, instead add multiple operators at the same time in each iteration. So instead of a circuit like this, which is kind of sparse because of this way of constructing the circuit that ADAPT originally took, we're going to do what's called Tetris adapt, where you add as many operators as you can that give you large gradients, and at the same time they touch disjoint sets of qubits so that they don't interfere with each other. So this Tetris adapt it's kind of easy to see. It's going to compress the circuit rather naturally, and you can go and do simulations and confirm that it really does do what you think it does. So this is showing energy error as a function of both circuit depth and C-naught count. So you can see that in terms of circuit depth, which is the dotted lines here. So the blue one is Tetris adapt, the orange is the original adapt, where you add only one operator at a time, and you can see circuit depth goes down by a factor of 2 or more in this example. And then if you look at the number of C-naughts in the circuits, they're about the same in both cases. So you compress the circuit by adding more operators at each layer, but you're not actually adding more C-naughts overall. And then you can also do this trainability analysis that I showed you earlier, and it still works in the same way, and that ADAPT is always kind of staying close to the global minimum in the landscape of parameters. So you can put together all of these improvements. So I mentioned this Tetris strategy of compressing your circuit by adding multiple operators at a time in ADAPT. You can also use this new CEO pool that Mafalda developed. And then together with a few more strategies that we've developed in terms of cutting down on measurement counts. I think Mafalda will talk about that in more detail in the next session. If you put all this together, then over 5 years, we've reduced C-naught counts and circuit depths rather dramatically by orders of magnitude. So I think in these small molecule examples, you can get several orders of magnitude reduction in all of these quantities. So that's kind of the current state of the art with ADAPT VQE. So right now, I think we're at the point where we can start to solve moderately sized molecular problems on current hardware. We're about, at the level of a few thousand gates to solve some of these more complicated molecules. So we're still looking to see if we can push things even further to do better. But now let me move on and talk about using these ideas to do something like Gibbs state preparation. So this is a problem that we heard quite a bit already about in this conference. So in this version of the problem, I'm given a Hamiltonian and a temperature T, and my goal is to simply prepare this state on a quantum device. And standard approaches run into challenges, namely that if you're trying to minimize the free energy, it can be really hard to measure the entropy, for example, on your device, which is a problem. And it's also hard to know what sort of ansatz that you should use, which is always the case, I guess. So we're going to try to use adapt to get around that second issue, let the problem tell us what circuits to use for this. We'll get around the first problem, the difficulty in measuring entropy, by changing the cost function. So instead of trying to minimize the free energy, I'm going to try to minimize this cost function, which also has as its minimum value the Gibbs state that we're trying to find. Now, rather strangely, this cost function depends on the target density matrix, the Gibbs state that we want, which seems like kind of a paradox. But what we're going to do is just use a perturbative expansion of this density matrix and use that in our cost function. And I'll show you that that actually works pretty well. And now this cost function is nice because all I have to do is measure powers of the Hamiltonian, expectation values of powers of the Hamiltonian. That's the first term. And then the second term is just the purity of the state, which is straightforward to measure. And we're going to do this by using an ancilla in addition to our data qubits. And that ancilla register has to be at most the size of the data register, of course, depending on the temperature T. And now we're going to use for our operator pool all possible 1 and 2 qubit Paulis on combined data and ancilla systems. So here's an example where we run this Gibbs adapt VQE algorithm on this periodic XY Hamiltonian on 4 sites with 4 ancilla qubits, up to 4 ancilla qubits. And the dots correspond to our solutions for the fidelity as a function of the temperature. And you can see the solid lines here correspond to the absolute best you could do given the size of the ancilla that we allowed the system to have. So you can see that for all ancilla sizes, adapt basically saturates the highest possible fidelity value. And then if you go to the full n equals 4 ancilla size, you get perfect fidelity essentially. And then compared to previous methods, our approach gives fewer C naughts, especially in the regime of low temperature, which is notoriously difficult. So I'll finish up my discussion of Gibbs just by saying that you could also do different cost functions, especially if you want to try to worry about things like variant plateaus. So there's been nice work by people in the audience where you can instead use the Renyi divergence, which is nice because it's an unbounded cost function, which means that even if you're far from your target solution, the gradients will still be large. And so we did some initial tests of this idea in our Gibbs adapt VQE algorithm. So there's this recent preprint by our group where we found that if we use this cost function based on the Renyi entropy, then as we go to large system sizes, the initial gradient norm stays almost constant, whereas other cost functions have this expected dip with system size. Okay, so I'm running out of time, I think, so I'll just take a minute to tell you about this control VQE work, which has a very different flavor. So what we want to do here is get rid of the gates and instead optimize pulses directly. Right, so any circuit that we come up with, whether it's in a fault-tolerant regime or near-term or whatnot, at the end of the day, what happens in the experiment is you take those gates, you turn them into pulses, and you apply the pulses to your device. So the idea here is, can we cut out the middleman and just go straight to the pulses? And I'll give you what I think are pretty compelling reasons why this makes a lot of sense. Okay, so that's basically what these slides are saying. So, every gate is made up of some sequence of electromagnetic pulses that get sent to the device. Like IBM uses these microwave pulses. So we want to throw out the gates and optimize the pulses directly. And an important thing to note here is that when I'm optimizing pulses directly, this is a generalization of the gate model. Right? Any gate base circuit that I construct corresponds to some sequence of pulses, but I can also come up with many more sequences of pulses which you've not written down in terms of gates. Right? So the gates, all the gate stuff that we do is just a special case of this more general landscape of parameterized pulses. So there's a huge amount of freedom that is not being exploited when we think about gates. And the question I think that is important and that we're focusing on at Virginia Tech is how do we take this pulse-based idea and find efficient ways to parameterize pulses to reach target solutions. So here's a simple approach that you can take, which is suppose you have some quantum device. Maybe it's a transmon type device like IBM has. You send one pulse to each qubit, and initially you just pick pulse values that will lower the cost function as much as possible. And now just randomly split your pulse. So initially you just have one parameter per pulse per qubit, which is one parameter per qubit, which is the amplitude here. Now split your pulse in time, and now you have suddenly two parameters that you can optimize. And you rerun your algorithm, optimize those pulses, get a better solution, keep going. You just keep splitting the pulse and adding more parameters as needed, kind of like ADAPT does. You only add as many parameters as you need until you reach your target state. So we ran this for small molecular problems. And the most important thing here to note is that if I do a gate-based approach like UCCSD for these examples, for example, for lithium hydride, it takes 80,000 nanoseconds to reach the target state. If I instead do this pulse-based thing, it only takes 50 nanoseconds. So already for this small problem, I'm saving 3 orders of magnitude in time to solution just by throwing out the gates. And this should actually not be surprising, because if I solve a chemistry problem, most chemistry problems do not have ground states that are highly entangled. They have a little bit of entanglement. It's just really hard to nail down that little bit of entanglement computationally. If I make a circuit that's built out of C0 gates, which are maximally entangled, and I keep doing a lot of entanglement, then I undo all the entanglement, I do a lot more entanglement, I undo all the entanglement. I'm doing this rather jagged walk through Hilbert space through all of these highly entangled states that are irrelevant for my problem. And if I throw out the C0s, if I stop requiring these pulses to implement these maximally entangled gates, I get much more quickly to the solution I'm after. So there's a much more direct path in Hilbert space, and it's not based on gates. And you can actually explore what's called the minimal evolution time, also known as the quantum speed limit, which is just the fundamental limit it takes you to evolve some given quantum state to some other quantum state under some Hamiltonian. And in our algorithm, you can keep reducing the overall time that you're giving the algorithm to find the state until you hit a wall, beyond which there is no longer any solution, because this is the minimal evolution time. So you can actually take your device, take your problem, and answer the question, what is the shortest possible time to produce the solution, given the device, given the problem? So that's a question that we're really interested in trying to understand more generally. So I think with that, I should probably wrap up. So here I'll just put my summary up, and I'm happy to take questions. Let me also acknowledge the people that did all the work, our students and postdocs. And also I'll just briefly mention that we have this new center in quantum at Virginia Tech. There are 15 or so faculty now working on various aspects, and we're always looking for good people. Yeah. Thanks.
Right, thank you, Ed. We've got time for a couple of questions, and I can see a hand up there already. If we can get a mic over there.
Hello, thank you for the very nice talk. At the end of the talk, you mentioned that you're using Pontryagin control principles to optimize the pulses. Can you elaborate on that, how you do this?
Yeah, so this control VQE algorithm is very close to quantum optimal control. You know, in some cases, you could think of it as just an example of that, right? Maybe the cost function that we're thinking about is not really common for, you know, typical quantum control practitioners, but it very much is along those lines. I would say what's important here is to figure out optimal pulse parameterizations. I didn't talk much about this, but if you do naive things like just send in one pulse per qubit and have each pulse have an amplitude and a phase and whatnot, that's by far not the most efficient way to get to your target state. So we're working on ways to sort of tie parameters between different pulses acting on different qubits together. So you have still a few parameters, but somehow the ansatz is much more knowledgeable about the part of Hilbert space that you actually care about.
Hello. You said in the end that there's very low entanglement in the states that you're trying to find.
Right.
Does that imply that your circuit should be even shallower than you're using right now, or do you have more or less like a notion of the limit of CNOTs that you can remove?
Yeah. So I think. So in this control-based algorithm, we're basically answering that question in the sense that we're finding the minimal time to solution. You know, since I've thrown out the gates, it's no longer a matter of how many CNOT gates do you need. It's a matter of how much time do you need. But in chemistry problems, it's well known to quantum chemists that most molecules of interest, you know, Hartree-Fock gets you 90 to 99% of the way to the target state. It's that last 1% that's the killer. And that's showing you that the target state is not very entangled. It just has enough correlation that it's out of reach.
All right. If we don't have any other raised hands, I'd like to thank Ed again, and we'll move on to the next speaker.